Hi, thanks for joining us for Phosphorus Science Now. I'm Matt Schultz with the Sustainable Phosphorus Alliance. One way to recycle phosphorus is to land apply the residual solids from wastewater treatment processes, or biosolids, to feed crops and stabilize soils. A fraction of the phosphorus that's applied is taken up by plants, and the rest remains in the soil where it may feed crops in the future, or it may leach or run off the land and become a pollutant to nearby waters. Sandy soils, such as those found in parts of Florida, have little native capacity to store phosphorus for the long term. Understanding the dynamics of phosphorus release from such soils after treatment with biosolids has implications for managing biosolids application and is the topic of a new agricultural and environmental letters paper. I spoke with its lead author, Dr. Yang Lin from the University of Florida. Well, Yang, thanks so much for joining us for Phosphorus Science Now. I'm interested in hearing more about your paper. Maybe you could tell us a bit about your collaborators and where you get your funding.
Oh, thanks, Matthew, for the invitation. Hello, my name is Yan. I'm currently an assistant professor from University of Florida. So today I'm going to show this paper recently published in Agricultural and Environmental Letters, where we compare the phosphorus release from fresh and legacy soils amended with biosolids. I want to highlight the folks who did most of the work here, including Bella Brush, who was an undergraduate researcher and completed her honor thesis in my groups on this project. Joanne is a graduate student in my group who doesn't like sharing her photos. And then we also have Michaela, another undergraduate researcher from my groups. Our co-author also include Todd Osborne from my department, as well as Rex Ellis and Andy Kenyans from the St. John Water Management Districts. So our funding sources include Florida Department of Environmental Protection, USDA National Needs Fellowship Grant, as well as USDA Hatch Grant.
Okay, great. So if you could go ahead and just tell us a little bit about the work you did, that'd be great.
Yeah, so biosolids are treated sewage sludge. They are commonly used as soil amendment because they are enriched in nutrients such as nitrogen and phosphorus. So here in the figure on the top, you see the biosolid material were compiled it in kind of this composting locations, which is quite common to stabilize these materials. In the figure down below, you see biosolids are applied to land. However, repeated application of biosolids could cause environmental risks and water quality problems. So here I'm showing you a study published by our co-author Andy Kenyon and his colleagues, where they compared the water quality records in these areas in Florida known as the Upper St. John's watershed. So, due to change of state policy right around year of 2013, a lot of the biosolid material that was previously, that were generated in the South Florida region, such as Miami-Dade, got applied into this watershed. So here they're looking at long-term water quality records from 1995 all the way to 2020s. And I'm selecting two of those locations to show you. 10 miles refers to this location number 5, and Penny Wash are this number 7 here. So what we are seeing are the total phosphorus in these streams watered, measured annually, and how that changed over times. And what we see is that right around the year of 2013, there was a very sharp increase in phosphorus levels in 10 miles as well as in penny washes over here. And the timing coincided with the enhanced and the consolidated application of these material in this watershed, which made us believe that indeed phosphorus was likely a main source of phosphorus enrichment in these stream waters. There are a lot of different factors that could govern phosphorus release from these soils, including, how much biosolids was applied, in which form these phosphorus existed in biosolids, as well as soil and hydrological conditions. But in this study, we're interested in the impacts of kind of aging, which means how long the biosolids had been applied to these soils. This potentially matters because past study has documented that in biosolid material they've been applied for a long time, the heavy metal tends to be more stabilized, suggesting that the aging of that material could stabilize these environmental contaminants. But very little do we know the effects of agings on the mobility of phosphorus. So in this study, we identified soils from the Upper St. John watershed, and they differ in terms of their biosolid application history. So we have a few soils, we call them Legacy 1, 2, and 3, where the biosolid application has ended in, like in the case of 1 and 2, the application ended in 2008. This has resulted in really elevated amount of phosphorus that we can measure in Mehlich 3 solutions. And the two soil has similar level of Mehlich 3 phosphorus, but they differ in terms of the aluminum and iron that are very important sorbent of phosphorus, and thus they have a different phosphorus saturation ratio or PSR. So along with these legacy soils, we also have one soil that has received continuous and recent biosolid application for right around a decade. And this has also resulted in significant amount of phosphorus levels, but slightly lower saturation ratio. So, by the way, I want to mention that all of these soils are really, really sandy with sand content right around 95%. So it is quite alarming to think about, right? How could these phosphorus be stabilized in these really sandy soils? Nevertheless, our teams took these soils and repacked their surface soils to their similar bulk density in these PVC columns. And and we leach them with around 100 millimeter of deionized water over 8 hours. And this leaching is comparable to a relatively heavy rainfall events that we typically see in Florida. And we applied this leaching twice a week for a total of 40 weeks because we're primarily interested in the longer term trajectories of phosphorus released among these soils. So moving on to the results, here what I'm showing are the orthophosphates measured by molybdenate blue methods in the leached water over the 80 leaching events. So first I wanted to guide you to look at this active soils in purple. And what we see is that it has a very distinct peak of phosphorus in the leachate, as high as 30 milligram phosphorus per liter. And then right after about 10 to 20 weeks, this peak of phosphorus quickly diminishes and then stabilizes for the rest of the experiment. This pattern is very different from the two legacy 1 and 2 soils in red and in green, where you see the phosphorus level in the leachates remain quite stable over the entire experiment. And Legacy 3, having the least amount of Mehlich 3 phosphorus, had an early peak, but then essentially the leachate concentrations of phosphorus remain the lowest across the entire experiment. Another thing I want to mention is that orthophosphates accounts for over 85% of the total phosphates, which is consistent with our past studies and that in biosolid material, inorganic phosphorus tend to be the dominant form the phosphorus existed. We could also sort of express the data also in terms of cumulative forms. So again, horizontally, we have the 80 leaching events, and then I'm showing the cumulative loss of total phosphorus now. And then we fitted the data to a so-called two-pool kinetic models. So the two pools differ in terms of their mobility. The labile pools tends to deplete fairly quickly uh, within weeks to months, but the fixed pool is more stabilized and can persist up to decades.
And
And
yeah,
both
so
of the
sorry to interrupt, but the fixed
no,
pool would include both maybe organic phosphorus forms and also inorganic phosphorus that might be bound to aluminum or iron, for example, right?
Yes, Matthew, exactly. So all of these will be, we will consider them as the fixed pools.
Great, thanks.
Uh, And both of them follow a kind of a first order decay that we can capture over here. And the model actually also predicts this kind of a gamma coefficient corresponds to the proportion of the Labelle pool. And we can see that the curve over here depicts the predicted pattern of these two pool models. And we see that the two pool model actually capture the release dynamics and out of these soils fairly well. And again, I think this figure highlights the differences between these soil with recent biosolid application in purple, as it has a really large peak, really a lot of phosphorus release early on, and then essentially stabilizes. Whereas in these two legacy soils, we have sort of a quasi-linear release of phosphorus that's just really persistent um, over time. And these patterns are also interesting because they capture the long-term release trend. Let's imagine if we were just stop our experiment right around, a rounds of 20, we would expect, oh, a lot of the phosphorus will continue to be leaching from the active, soil without recognizing that these phosphorus release in the legacy are actually pretty consistent for the long term. So again, I think this highlights that in order to better understand the fate of these phosphors, we should actually consider adopting longer terms studies. Also, lastly, our results we wanted to look at the output from these models. So here we have this coefficient depicts the size of the labile pools. So we can see in both of those legacy 1 and 2 soils, only about 2% of soil total phosphorus can be considered as a labile that is quickly mobilized by water, while the rest of the are released more slowly but consistently in contrast to the active soil. I also want to guide your attention to the rate, essentially the release rate of phosphorus of the fixed pool. And we see that in both legacy 1 and 2 soil, the release rate is roughly an order of magnitude lower than the one in the active soil. And we interpret this as this long exposure of biosolid in the soil and specifically aging can reduce the mobility of phosphorus and essentially leaving them there longer, right? Meaning that it takes a longer time to completely leach out these phosphorus. We did some back of the envelope calculation using this data, and we believe that in order to remove about 80% of these phosphorus in these legacy soils, it would take either, as short as 20 years, but it might as well take up to 100 years to completely remove that phosphorus, which is quite um, surprising given the fact the soil material is really, really sandy. So we believe that the longer term stability is partly due to aging and also partly due to the alkaline nature of the biosolid materials that these heavy lime stabilization during the biosolid production processes has remained in these soils and they can help to stabilize these phosphorus. To conclude, what we found is that the fresh, recently applied biosolid really show a distinct phosphorus release pattern compared to the soil that receives a legacy phosphorus. So in these, recently applied soils, phosphorus could be released relatively quickly, but the remaining phosphorus in the aged biosolid is really more consistent is more resistant to leaching even in highly sandy soils. And it may take decades for the phosphorus can be completely depleted. So overall, we identified that the exposure time to soil is a really crucial factor for understanding phosphorus dynamics.
Great, thanks so much for that explanation, Yang. I wonder, one question I had was, so you used deionized water in your columns. Um, do you have a sense of the pH difference between that and the rainwater that you're receiving in Florida, and um, whether that would have anything to Any effect on the leaching?
Yeah, that's a great question, Matthew. The rainwater that we have in Florida, Florida tends to be slightly acidic, right around pH of 6. The DI water that we used has about a 6.5 differences. So I think if we mimics the pH of the rainwater, we may discover slightly faster loss of the phosphorus, given that some of those biosolid material are alkaline stabilized. But I think uh, that differences in pH probably wouldn't affect our estimate of their persistent, uh, just because the differences in pH between the DI water and the rainwater is still relatively small.
Right. And then can you maybe comment on sort of the management aspects of your findings? So, I hear often that, biosolids, once they're applied, they kind of release phosphorus, but then the rest of the phosphorus that's bound to alum and ferrous, especially, is locked up. It's not going anywhere. But
Mm.
your study really shows that there is this long-term legacy phosphorus release. So I wonder if you have any thoughts on phosphorus management in that context, in the context of biosolids land application.
Yeah, of course. Thanks for the question. Actually, we're continuing our works with our colleagues at the St. John's Water Management Districts, and we're looking at several potential remediation strategies to kind of immobilize the phosphorus. So one of the things that we're working on is to introduce amendments to stabilize biosolid before even applying them in the field. So we're looking into, for instance, the aluminum or iron-based drinking water treatment residuals as a potential amendment. Um, Another way to look at this will be to try to intercept the phosphorus released from these material before they reach surface water. So we're looking at things like edge of the water amendment or targeted facilities that we can intercept these kind of a phosphorus. But as you said, the loss of phosphorus in these really sandy soil is likely to be happening over a long period. So that will require kind of our continuous attention, both on research but also for management.
Okay, great. And a last question, just to be clear, the biosolids that were applied were already treated with either alum or ferrous, is that right? Or do you know what they would be?
Yes, we know that in the Legacy 1 and the Legacy 2 sites, these biosolids was stabilized by lime. Calcium carbonate kind of a material.
Okay.
In the active soil, we believe that was partly stabilized by aluminum,
Okay.
based off the um, records that we had as well as the soil testing. However, for the Legacy 3, we wasn't really sure because sometimes locating the exact documents and the source of the biosolids could be very difficult, especially in these legacy sites.
Okay, sure. Okay, well, thanks so much.
Oh,
I
thank you so
appreciate
much, Matthew. It's a great pleasure talking about our research.
it. Great. Take care.
Take care.